again, with finding mins and maxes, there are a couple different strategies. This is the strategy I'm going to focus on more today. I don't think we're going to get to Lagrange multipliers today, but it's another method of determining where mins and maxes occur on surfaces. This method also allows you to find saddle points. You can often figure out that there must be a saddle point due to your Lagrange multiplier not directly working out to help tell you a min or max, but really you use the method of Lagrange multipliers when you're pretty much just looking for mins and maxes and you know they exist, whereas this is more if you're investigating the curves in general. So the first thing that you do is you find the critical values of your surface. We're going to apply to three-dimensional surfaces, but again, the principles do apply with higher dimensions. It's just harder to, it's more complicated, but the basic principles still apply. But we're going to stick to 3D in our class. So you find critical values. The critical values are defined like they are in Calc 1, where the first derivatives are equal to 0. But because we're now in 3D, I have a derivative with respect to x, and I have a derivative with respect to y. And a critical value, for the purpose of what we're doing here, a critical value is a critical value only if both are 0. Okay, so you're not collecting numbers where one's 0 and then adding to that set where the other's 0. You're only looking for values that make both 0 at the same time. Okay, and those are your critical values. So we know the first and second derivative are 0 at these specific values at the same time. So for any critical point, you're going to calculate this value that we're going to call D. And D is a difference between the product of the second derivative with respect to x with the second derivative with respect to y minus the partial with respect to x and then y squared. Okay? Exactly why we're doing all this, you know, is a combination of algebra and geometry analysis. At the moment, why don't we just kind of accept that we're going to calculate this thing called D, and there's its definition. If D is positive, then we're going to end up with either a minimum or a maximum. So if D is positive, you're going to end up with a minimum or a maximum. You'll end up with a minimum if f sub double x or f sub double y is positive, because your graph will be concave up. If your second derivative is positive, your graph will be concave up, hence you'll be hitting a minimum value. If your second derivative with respect to xx or yy is negative, then your graph is concave down and it's indicating that you've hit a maximum. Now I will point out, if you go back to the formula for D, if it is positive, so we already know D is positive, okay, we've identified D as positive, then whatever sign this is, this has to be the same sign. So you don't need to check both f sub double x and f sub double y if you already know D is positive. You can pick whichever one you want to test. Do you see why we know that these have to be the same sign? If they weren't, what would be the sign of this product?
It would be negative.
It would be negative, and then you're taking negative minus something that we know has to be positive because we're squaring it. D would have to be negative. Okay, if f sub double x and f sub double y are different in sign, then D has to be negative. So if D is positive, then you know that these are the same sign, and you know that this product is bigger than this, and it turns out that where you hit maxes or mins, that product is always gonna be bigger than the partial derivative of x and then y. Again, if you look at the algebra and the geometry, you can kind of see that. So if D ends up being negative, that means that f sub double x is one sign and f sub double y is the other sign. And so you end up getting a saddle point, because you have one direction and then the other direction gives you a different curvature. Okay, so like we don't have to test f sub double x or f sub double y, because if D is negative, we know they're opposite signs, thus we have a saddle point. Okay, so you only test f sub double x or f sub double y if D is positive, and you're doing so to determine if you have a min or a max. If D is negative, you just automatically know you have a saddle point. If D is 0, then you have to do more investigation, because you could have different reasons why it's 0. It could be 0 because it's so flat that you don't have any curvature. It could be 0 because your algebra is just, or it could be 0 because it's linear. It could be 0 because it's not linear, but it's really, really flat. So basically, you have to kind of look more deeply into your function to figure out what's going on. Alright, so then I put a bunch of examples together, and with your examples, I've graphed the function, and along with the function's graphs, I've also shown the level curves, and the level curves are helpful in terms of identifying mins and maxes also. So, for example, this Mexican hat type curve, it has a minimum, which we can't see, it's like down in the bottom of the hat. But from the level curve, you could see how, kind of like a bullseye, it's bullseyeing in around where the minimum is. So we'll go through the process and prove that we have a minimum there. Okay, this curve, can you guys see that it does have two maximums. And so the two maximums are showing up in these circular parts of the graph. If I actually had drawn a contour map that had more level curves in it, there'd be another little circle here, more narrowing in on here. But notice how the contours cross over each other. Guess where they're crossing over each other? At the saddle point. So you can see that this graph has a saddle point here. In this direction, it's concave up, but in this direction, it's concave down. And if you look at a level curve, that'll show up by the contours crossing over each other. This curve has two maximums and a minimum, so you can see them here. This is one of the maximums, this is one of the maximums, this is a minimum. Without numbers on my curves, I don't necessarily know that this is a max. I know it's a max from also looking at the graph over here. But I do know that one or the other has a curve. So if you're looking at level curves, they're often helpful for you to narrow down, something's occurring here. If you had numbers on the contour, you should be able to tell if it's a min or a max. This just has one maximum. You can kind of see where it's showing up here. And this has all kinds of goofy stuff going on, but we do have some subtle saddle points. And there are no mins and maxes. So there are some saddle points, but there are no mins and maxes. When we get to this one, I'll kind of point out. If you decided to cut this particular graph, like you decided, okay, these are my boundaries, my graph only exists within these boundaries, then you would have a maximum here, and a minimum here, and a maximum here on on the border. But if you leave it unbordered, then the graphs, the hills just keep going higher and higher and higher, and the valleys just keep going lower and lower and lower. So without a restricted domain, this function has no maxes and mins. And you can see that from the graph here. I don't have any circles, you know, circling my maxes and mins. And then this one has one minimum. You can kind of see it showing up. All right, so we have different things going on in our different examples. So we're gonna go through the process for each one, and some of them work out real nicely, some of them have messy algebra.